Okay, so in the previous video, we solved the differential equation for a charging RC circuit. So we found QC as a function of time. That's the charge on the positive plate as a function of time. Once we have that, once we have QC as a function of time, we can calculate everything about the circuit at any time. For example, we can find the current. How do we find the current? Well, we saw before that this is given by, the current is just given by the derivative of QC with respect to time. Remember, this is for the case of a charging circuit. In the case of a discharging circuit, we add the minus sign here. Okay, but now we just take a derivative. So we just take the derivative of QC as a function of time. And here in parentheses, you have QC as a function of time. I just rewrote it in a slightly different form. Before it was written as CE times, in parentheses, 1 minus the exponential. But here I just distributed the CE. So we have this. So this is QC as a function of time. The first term is a constant. So it doesn't change in time. So the derivative with respect to time of that will give us 0. And then here we have to differentiate the second term here. Minus c times e is a constant. You can move that in front of the derivative, and you just have to differentiate the exponential here. And for that, we use the chain rule. So again, what I did is that I said the derivative of this term here will give us 0, so I don't have to worry about this term here. And here I moved the minus ce in front. The derivative of the exponential here is the exponential multiplied by the derivative of the exponent. And the derivative of minus t over tau, remember tau is a constant, and we differentiate with respect to time. So the derivative of minus t over tau is just minus 1 over tau. So if I multiply everything together, I get this. That's it. That's the current as a function of time. We can rewrite it in a slightly different form. Remember the tau here stands for R times C. So if I write tau as R times C, I can, so it's R times C, I can cancel out the C, and I'm left with E over R times the exponential. This is the current as a function of time in the charging circuit. Notice that the charge was growing, so remember this function here, this is QC as a function of time. The graph of this as a function of time was an increasing exponential that tend toward an asymptote, a constant value equal to CE. For the current, we have a decreasing exponential. Current starts high, large, and then it decreases exponentially with time. Clearly, the maximum current is at t equals 0 because we have a decreasing exponential. And what's the value of the maximum current? Well, at t equals 0, if you set t equals 0 here, you get e to the minus 0 here. So this is just 1 here. So you're left with E over R times 1. So the maximum current is just E times R. Okay, this is the maximum current, and it occurs at t equals 0. You always have that when you have a decreasing exponential. This is a decreasing exponential. The term that multiplies that is in front of the exponential here is the value at t equals 0, and is the maximum value of that quantity. So E over R is the maximum current that we have. Okay, so to summarize, what we had was that we have the charge as a function of time. Again, when you have a curve of that form, 1 minus an exponential, you get an exponential, an increasing curve that tends toward the constant. And the maximum value is reached at t equal infinity and is equal to C times E. The value in front here of the parenthesis is the maximum charge reached at t equal infinity. When you have this form here, you have a decreasing exponential this time, and the maximum value is here. It's E over R, and is the value at t equals 0. Once we have the current and we have the charge, we can also find the voltages in the circuit. For example, if you want the voltage across the resistor, you just use Ohm's law. So you do R times I. So multiply this function here by R, and you get E times, the EMF times E to the minus t over tau. This gives us the voltage as a function of time across the resistor. Notice that this is a decreasing exponential. You start with a value equal to E at t equals 0, and it decreases exponentially towards 0 at t equals infinity. That makes sense because the current starts large, and the current decreases exponentially, goes to 0. Therefore, the voltage across the resistor also starts large and decreases exponentially towards 0. Okay? Now, we also can find the voltage across the capacitor. We just use, remember for capacitor, the voltage across the capacitor in absolute value is QC over the capacitance. So you go back here and you take this function here, which is valid at any time, and divide that by the capacitance C. So you just divide by C, you get rid of the C here, you're left with this function here. And again, the voltage across the capacitor this time is an increasing curve. It goes like this here, it goes up, 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 and tends towards a constant at t equals infinity. That makes sense because the charge is building up on the capacitor, so you expect the voltage across the capacitor to rise and tend toward the constant. So we always have either one or the other of those two curves here. Whenever you have a form like this of 1 minus e to the minus t over tau, you get a curve of this form here. If you have a form like this, a constant times a decreasing exponential, you get a curve like this. So in our case, the current, okay, the current and the voltage across the resistor, they follow a curve like this. Whereas the capacitance, the charge on the capacitor and the voltage across the capacitor, they follow a curve like this. Now, when I say they follow a curve like this, I mean they have this shape, but they, of course, they tend toward different values. If you look at the charge on the capacitor here, as t goes to infinity, it approaches C times E. So this is the value of the charge reached on the positive plate of the capacitor as t goes to infinity. So if you were plotting this curve here for the charge on the capacitor, it will tend toward a value equal to C times E. If you look at the curve for delta VC here, it tends toward a value equal to the EMF. Here in this graph, they wrote V0 here. Here, this is actually, they mean the voltage across the capacitor. And here by V0 here, they really mean the EMF. Okay, so that's what we call the EMF. For the current and the voltage across the resistor, you have decreasing exponential. You start at the maximum value. Again, this maximum value is different for the two curves. For the current, you start at a value equal to E over R. That's the initial current, which is the maximum current. And for the voltage across the resistor, you start with a value equal to the EMF E. And that's the initial value, and that's the maximum value of the voltage across the resistor. And then you have a decreasing exponential. So you have those two curves here. Okay. Now, just a last comment about these equations. Notice that if you look at the voltage across the capacitor and the resistor and you add them up, and here I'm really adding the two values at any time. So this is the voltage across the capacitor at any time, and I add that to the voltage across the resistor at any time. Notice if I distribute the E here, I get E times 1 minus E times the exponential here. This term here multiplied by E here will cancel out this term here. So these two terms cancel out completely, and when you add them up, you just get E. You get the EMF of the battery, and it's a constant, right? It's a fixed number. So even though this voltage here is a function of time and this voltage is a function of time, what this equation is telling us is that when you add them up, both of them keep changing with time. Delta VC keeps, well, you know delta VC is increasing in time, delta VR is decreasing in time, but it turns out when you add them up, you get a constant. And you expect that because that's something you expect from the voltage, the loop rule, right? The loop rule was telling us that the voltage across the capacitor plus the voltage across the resistor has to be equal to the EMF at any time. But what this is telling us is that the voltage across the capacitor here is increasing and the voltage across the resistor is decreasing, but the two changes are compensating each other exactly. So if, let's say, you take a certain amount of time, let's say in 1 second, the increase of delta VC would be exactly equal to the decrease of delta VR in the same amount of time, so that the sum is always equal to the EMF. So really, you get a curve like this, and you could check that if you are plotting, this is here the voltage across the resistor as a function of time, which is decreasing exponentially. And here you write it as a percentage here, but the percentage here, this is for the voltage across the resistor here, we start with a value equal to E, the EMF E. And if you look at the voltage across the capacitor here, this one is increasing and it tends towards the EMF as t goes to infinity. But if you are plotting the two curves and you are adding up the two curves at each point, you will always get a value equal to the EMF. So the decrease of the voltage across the resistor is compensated by an equal increase of voltage across the capacitor, so that the sum is always equal to the EMF. Okay, don't worry about all the information here. They talk about something a bit different than what I'm talking about, but I want to focus on those two curves as being the voltage across the capacitor and across the resistor. So they add up to the EMF. Okay, so it's important in those circuits to be able to tell if just based on physical reasoning, what type of curve you expect for the different quantities. If you have a charging or a discharging circuit, do you expect to have a curve that goes up like this here and that plateaus like this? Or do you expect to have a decreasing exponential here when you talk about, let's say, the charge on the capacitor or the current or the voltages and so on? You should be able to know what to expect without just looking at the equation. You should have some physical intuition for which curve makes sense for the various quantities we're talking about. Okay, thank you.